28. Okay, I have the pleasure of introducing Prof. Giuseppe Caire, who is currently the Alexander von Humboldt Professor at the Faculty of Electrical Engineering and Computer Science at Technical University Berlin. He has a long biography. I'm just going to pick a few of things. He did his BSc at Politecnico de Torino, his MSc at Princeton, and a PhD at Politecnico again. And he did a postdoctoral research at the European Space Agency and became an assistant professor in telecommunication and at Politecnico, associate professor at University of Parma, and became a full professor at the European Institute in France. He has been also a professor of electrical engineering at Vitaby School of Engineering, University of South Carolina, in South California in Los Angeles, and currently he is the Alexander von Humboldt Professor at the Faculty of Electrical Engineering and Computer Science. He's received a couple of awards. If I'm going to be going through all of them, we will take half of the time of the talk, I suppose. He's won a couple of paper awards, including the IEEE Communication Society Information Theory Society Joint Paper Award in 2004 and in 2011. He's got the Okawa Research Award, the Alexander von Humboldt Professorship, the Vodafone Innovation Prize in 2015, and the ERC Advanced Grant. Yes, he's going to be talking to us today about the mathematics of massive random access communications. Yes, Giuseppe, you can take it up from there.
Thank you very much. Thank you very much. And it's a pleasure to be here. Thank you, Bubakar, for inviting me. And okay, so this talk is about massive random access. But first of all, I'd like to acknowledge some collaborators in my group in Berlin, in particular Said Hagiachoar, who was a postdoc and now he left and he's working in Switzerland. Peter Jung, who is also senior postdoc associated with my chair, and Alexander Fengler, whose work is mainly represented here towards the end of the talk especially, who is a PhD, is a graduating PhD student. He will defend in a month or two. Okay, so the plan for this talk is to first point out some concept about a multiple access channel in information theory. So what it is and how has been treated so far in classical information theory. Then I will introduce a problem that is fairly recent in the last few years. It's called unsourced random access, and the motivation and the problem definition. Then I will relate this problem with something called coded compressed sensing. Has to do with compressed sensing or sparse estimation. I will present a generalization of the problem to the case of multi-antenna receivers that introduces an interesting mathematical aspects and some new algorithms for which we can characterize scaling laws and how they behave. And then I will just mention in passing, because it's too much and it's really work in progress, very, very, very recent, some relation to tensor decomposition. So there is a lot of interesting things going on here. Okay, so multi-access is, you know, in general, communication devices that want to share a common medium, for example, a common radio channel. And in particular, the multi-access channel in information theory is the channel from many transmitters to one receiver. So they would like to talk to the, for example, mobile phones, they want to talk to the same base station, and in general, they share the radio channel, which is a shared medium, so they have to somehow coordinate or not to coordinate to make them understood. So how people have addressed this problem in engineering? Well, for example, trying to make the users orthogonal in time, allocating different users to different time slots. And of course, this is very nice, but because it makes things very simple, it reduces the problem to a single user problem in every time slot, but it requires quite a good deal of coordination. Frequency division is the same thing, simply allocating different transmitters to different frequency subbands, or so-called CDMA, code division multiple access, or also non-orthogonal multiple access, where somehow every user spread encodes information over a wideband signal, and somehow they all interfere, and in any case the base station or the receiver is able to somehow separate the signals and still decode the information. So those are, you know, kind of like practitioner approaches, and then the question in information theory is, are these approaches principled? Do they achieve fundamental limits or not? So in information theory, we define a multi-access channel as a channel with several inputs. In this case, for example, I give the definition for two users. So we have two inputs with two different, say, alphabets, x1 and x2, and a transition probability that gives the output y as a given x1, given the input x1 and x2. And we define a multi-access code as basically the collection of all possible messages of user 1, all possible messages of user 2. So indices from 1 to 2 to the n r1, 2 to the n r2. R1, R2 are the transmission rates. If you take the logarithm, you know, take the log of the size of the message set for user 1, so you get basically n r1, then you divide by n is the block length, and you have the number of bit per symbol transmitted by user 1, the same thing for user 2. So we have two encoding functions, a function, an encoder for user 1, let's call it F1, that maps messages in the index set M1 into code words. So there are simply sequences of length n of symbols from the alphabet X1, an encoder function for user 2 that maps messages from the index set M2 to code words for user 2, and a decoder function at the receiver, which is a map that maps sequences on the output alphabet into pairs of messages. So the receiver basically has to produce two estimates of the transmitted messages based on the observation of n symbols from the output. And we can define the capacity region operationally as the set, in fact, the closure of the set of all rate pairs R1, R2, for which there exists a sequence of codes of rate R1, R2 and increasing block length, such that the probability of error vanishes as the block length goes to infinity. And what is the probability of error? The probability of error is simply for a given channel and a given encoding functions and decoder function. The probability of error is that the probability that the decision made by the decoder is different from the pair of messages that were transmitted by the users. So this is the classical information scenario, setting. And now the challenge, of course, is to find a theorem that says, okay, there is a region of rate R1, R2 for which these codes with vanishing probability of error exist, and there is a region, outside this region, these codes do not exist. So, of course, the existence part is called achievability. The non-existence part is called converse. And if you are an information theorist and you work on a problem, if you are very lucky, you find what is called matching, achievability, and converses, which means you can determine this region exactly. In this case, I have to say, in many problems involving more than one transmitter and one receiver, this region still escape analysis. There are many open problems in network information theory or multi-user information theory. But for the case of the MAC, we know everything, pretty much everything. And there are general formulas for general classes of channels that give us exactly this region, for which if you operate with the rates inside the region, there exist coding techniques that achieve arbitrarily low probability of error. If you operate outside, these do not exist. Now, this is different than finding these coding techniques. There is a big difference between proving existence and actually constructing. In information theory, most of the results are non-constructive because the achievability is typically obtained through techniques based on what is called random coding. Random coding means instead of constructing explicit codes, you consider randomly generated codes and then average over the ensemble of those codes, and then prove that the so-called ensemble average probability of error goes to 0 when the length goes to infinity. And then if the average over a randomly generated code goes to 0, the average probability goes to 0, it means that there exists at least one sequence of deterministic codes for which the probability of error goes to 0. So in this way, you prove existence of codes with arbitrarily small probability of error without constructing them, because constructing them is extremely complicated, and this pertains to coding theory and to algorithms, coding algorithms and decoders. So anyway, this to give you a little bit, the story and the background for those of you who are not maybe so acquainted with the information theory and the information theory type of reasoning. Now I'm going to focus on a very simple model, which is called the Gaussian MAC. The Gaussian MAC is described by simply this input-output equation. I still make the example of two users. The channel is real and additive, so the input symbols are real numbers, x1, x2 are input symbols. The channel simply create a linear combination of these real numbers through coefficients, let's say G1 and G2, which are assumed to be known, and describe, for example, the attenuation through a transmission channel. And the channel adds a Gaussian random variable, which is noise. So the output of the channel Y is conditionally Gaussian given the input. And in fact, you can write the probability P of Y given x1, x2 is a Gaussian density of little y given little x, little 2. Well, this will be essentially the density of the Gaussian distribution with conditional mean G1, x1 plus G2, x2, and variance equal to the variance of the noise, which we typically denote by n0 half. In the case this is real. There is also a version of this channel for reasons more connected to actual communication theory, for which we like to use in phase and in quadrature components, so real and imaginary part of complex numbers. So you have a complex version where the noise is a complex circular symmetry, but I will not get into these details. It's not very important. We can just focus on the real case for simplicity. So, of course, the capacity of this channel would be infinite, because it's clear that if we don't put any constraint on the input, since the input are real number, which is an uncountably infinite and unbounded alphabet, well, I can pick points that are infinitely apart, and so communicate all the information I want without never making an error. So in fact, for a matter of practicality and actually real life, we constrain what is called the average energy per symbol of the transmitted code word. So 1/n sum of the magnitude square of the symbol. So this is essentially the normalized 2 norm square of the code words, must be less or equal than some quantity that I call energy per symbol for user K. And this has to be true for all the messages of user K. It means that basically the code words live in a hypersphere in n dimension, whose radius here is simply square root of n times ES. So you may imagine geometrically code words are points on an n-dimensional sphere with a given radius, and the square of this radius, in fact, is the total energy of the code word. If you divide by the dimension, this will be the energy per symbol, which is, of course, when you multiply by the bandwidth, so the number of symbols per second, it becomes power, so energy per unit time. So this sort of quadratic constraint is very practical. It means basically that the user cannot transmit unlimited power. And it turns out that in this case, the capacity of the two-user Gaussian multi-access channel is described by these regions. So of course, the rates are non-negative. So there is always here, they're all non-negative quantities. But essentially, it's a region that looks like this. There is one inequality that governs the rate sum, and then you have two individual inequalities that govern the individual rate, and whatever is inside this sort of pentagon is achievable, and whatever is outside is not achievable. And this boundary, C of SNR1, C of SNR2, C of SNR1 plus SNR2, is simply, if you are acquainted with the so-called Shannon formula for the Gaussian channel, 1/2 log of SNR, or log of 1 plus SNR, is the capacity of a single user Gaussian channel. And this says that user 1 should transmit at a rate which is not larger than its own individual capacity. User 2 should transmit at a rate which is not larger than its own individual capacity. And collectively, user 1 and user 2 should transmit at a sum rate, so the sum of the two rates should not be larger than the capacity of a channel that has as SNR as the sum of the two SNRs. Okay? So this is the region, and the region has also some interesting interpretation. For example, the region has the following interpretation. There are two corner points here, and you see that all the points in this region are component-wise dominated by this segment, which is called the dominant face of the region, in the sense that at any point inside, well, you can pick a point here that component-wise dominates. So essentially, we are only concerned about achieving points on the dominant phase, because if we achieve points on the dominant phase, anything less than that is also obviously achievable. And particularly interesting are the so-called vertices or corner points. For example, if you consider this corner point, this one, and you consider the expression of this capacity C, well, you know, this is the equation R1 plus R2 less or equal than 1/2 log of 1 plus, let's say, SNR1 plus SNR2. I use S instead of SNR just for brevity. And this is the equation R1 less than 1/2 logarithm of 1 plus S1. So if I consider this coordinate, this point for R2, this is exactly R2. When these two lines intersect, I solve for R2, I find that this is 1/2 logarithm of 1 plus SNR2 divided by 1 plus SNR1. And this has a very nice interpretation. It means that in order to achieve this point, what we can do at the receiver, we can first decode R2 by treating the signal of user 1 as noise. So you see that this quantity can be interpreted as the power of user 1 or user 2 divided by the power of the noise plus the power of user 1. So we are treating user 1 as noise. Then we can subtract the signal of user 2, and now we can decode user 1 at its own individual capacity. So this is called successive interference cancellation approach. And by the way, these things are implemented today in certain actual systems. Okay, so this is not science fiction. It's a nice way to achieve the Gaussian multi-axis capacity by successive interference cancellation. Of course, in order to operate at this point, we need to coordinate the users, and we need to tell them, please, user 1, transmit at a rate R1, which is close to this 1/2 or 1 plus SNR1, and please, user 2, transmit at a rate which is whatever it is, this quantity, which is such that the successive interference cancellation works. If the two users do not coordinate, for example, and transmit at the equal rate point, which maybe is at a point like here, well, this becomes much more difficult to, we cannot decode one, subtract it, and vice versa, because treating the other as noise is simply the rate would be too large, and so it would make an error with a very high probability, and therefore subtracting interference becomes impossible. And therefore you have to use much more complicated decoders, which are called joint decoders, that simultaneously try to guess the message of user 1 and message of user 2, and then you can imagine that this type of joint decoders are much more complicated to implement. In general, if you have many users, the complexity of decoding, of joint decoding, becomes exponential in the number of users. So just to continue and finish this part, fortunately, this problem and this result generalizes to the case of K users. In fact, the K user Gaussian mach is simply, the K user extension of what we have just seen, and one can show that the capacity region is described by the set of inequalities. In fact, we have exactly, you see these, we have for every subset of the set of users, we have one inequality, apart from, of course, the empty set for which the inequality will be trivial, and therefore we have 2 to the k minus 1 inequalities. So this region is a polytope in k dimension with 2 to the k minus 1 facets, and every facet is defined by a hyperplane that corresponds to a subset of users. And so this is a very complicated region with an exponential number of hyperplanes. It's a convex region, and it turns out that this region has a nice structure. In fact, because this function as a set function, so say if you see this function C as a function of the set K is called a set function, and it turns out to be a submodular rank function, and therefore polytopes defined in this way have the structure of polymatroids. So for example, in 3 dimension, it looks like this, and then you can go on, and polymatroids have a very, very nice structure. For example, it is very easy to solve problems like, for example, if I want to solve a problem of the type max sum of W, K, R, K subject to R in the capacity region C. This is a linear function. These may be our weights. that give, for example, the priority of the users, and we want to maximize a weighted sum of rates subject to feasibility. So the vector of rates is inside the capacity region. And it turns out that this would be a terribly complicated problem because, okay, it's a convex problem because C is a convex polytope, and the function we want to maximize is linear. In addition, it's a convex polytope that so is defined by a set of inequalities. So this would be a linear program, but the number of inequalities is exponential in the dimension. So this would be hopeless in general to solve unless we have the special structure. And with the structure of polymatroid, the solution is very simple. It is sufficient to sort the weights in increasing order, and then basically the permutation that sorts the weight gives the vertex of the polytope that maximizes this weighted sum of rate. So this is just an example. Okay, I will not get into these details, but this is just an example to say that not only the information theoretic results are known for this channel, but also there are efficient schemes to operate very close to the vertices of this region, and every vertex of this region maximizes, for example, a weighted sum of rates, because every vertex of the polytope corresponds to a permutation of the indices, and in fact is the permutation that sorts the weights in increasing order, and then you want the vertex that maximizes this linear function is the one that corresponds to the decoding order, where you start decoding the user with the smallest weight first, and then so you basically decode in this direction. You start by the user with the smallest weight, and then you go on and you go on and you go on. In this way, you maximize the weighted sum of rate. Okay, great. So this is a story of the Gaussian multi-axis channel, for which we know pretty much everything. More recently, people have considered a new model called unsourced random access channel. And the motivation is essentially what is called a machine type communication or Internet of Things scenario, where we may have an enormous number of potential users, for example, devices, sensors, that only sends very sporadic data. So you may have 1 million of sensors around the city, and a big data collection center, a big tower mounted on the Fernsehturm in Berlin, for example, and only a handful, a few hundreds at a time will send their measurements, and maybe these measurements are just I don't know, 100 bits. So very, very short messages. And then you see that if we want to use all this machinery that I explained before, or any protocol that tries to make the users orthogonal, coordinate the rates and say, okay, now you transmit, the protocol overhead of such a thing becomes, in fact, overwhelming with respect to the data communication. So we are basically wasting more energy and more bandwidth to coordinate than to actually transmit information. So the idea was, okay, can we have a system where, first of all these users use the same codebook. If you remember before, in the classical information theoretic definition, I say, okay, there are 2 encoding functions, or in general, k different encoding functions, and every user has his own codebook, individually generated and at its own specific rate. But in fact, this is very impractical, because maybe you want to manufacture, very cheap devices that have hardwired in some chip or in some microcode an encoder, and this is the same for everybody. So same code book, and then completely uncoordinated access, which means at every time slot, a random set, typically very small set of these users will transmit whatever message they want, and the task of the receiver is to come up with a list of transmitted messages, no matter how. So the list of transmitted messages means that, for example, if a user wants to just transmit like a measurement, maybe you are only interested in some averaging. So you don't really want to know the identity of the sensor who is transmitting this measurement. Okay, so this will be just a bunch of bytes that represent this message. If a user wants to transmit his identity, well, he will simply put his address, unique identifier, as a part of the payload. So it's not distinguished. So in other words, we are reversing the two functions. In the classical MAC, the receiver knows who is talking, knows that there is user 1, user 2, user 3, they're talking, and each one of them uses his own codebook, which is known at the receiver, and the receiver uses this knowledge to decode. Here, the idea is that the receiver has to come up with a list of transmitted messages. The codebook is the same, so the identity of the user a priori is not known. And after decoding the messages, well, then the receiver will know if there is some information about the identity of the users. It will be encoded inside the payload. This problem was posed by a friend of mine who is a professor at MIT, Yuri Polyansky, who looked at first at a very simple model, which is essentially, again, a real adder Gaussian channel, where it's almost the same as before, The only difference here is that here, these code words all belong to the same codebook C, and the set A is the set of active messages. We do not know who sent them before decoding, okay? The task of the base station is to, or the base station, the receiver, is to come up with a list of messages, so implicitly also identify how many they are and come up with a list, which is in general a subset of all possible messages. I assume here that every message is formed by B bits. And then we define the per user error probability as simply the arithmetic mean of the probability that message K, active message K, is not, sorry, this should be not included in the list. Okay, so if message K is not included in the list, we say there is an error. And of course, there is also another type of error, which is a false alarm, where a message, the probability that the list contains a message that was not transmitted. And of course, there is also always a balance between misdetection and false alarm probability. Okay, so this problem is a bit, you see that now the total number of users has completely disappeared. All what counts is how many users are active at the same time. We don't care if there are 1 million, 1 trillion of users, because they all use the same code book. So as long as there are maybe 10 users that transmit, we need to come up with this list of 10 messages. And it doesn't matter how many devices have been manufactured in the universe. So it is not such a stupid model after all, if you think, like a mass production of like Internet of Things device. devices. So this problem has also a sort of compressed sensing formulation, because we may imagine like this. Imagine that we have this code book with 2 to the b possible code words and of length n symbols each. So we can stack the code words as columns of a matrix. So we have this matrix that contains all the code words, and this will be a matrix of dimension n times 2 to the b. And then we can have a vector that contains simply a 1 in correspondence of the messages that are actually transmitted, right? So this is a very sparse vector. And then, of course, we have noise, and then this will be our observation. And now you recognize immediately that this is a compressed sensing problem. So we want to somehow identify which code words are active, which means finding the activity pattern of this vector Q, find the ones in this vector of zeros and ones, which is in fact extremely sparse, because typically maybe we have, I don't know, in a practical case, we may have Ka some 100, and B is also 100 bits. So this matrix, in fact, I mean, this vector has 2 to the 100 components, and there are only a few hundreds that are non-zero. So the sparsity level here is enormous. And so in this way, you understand that trying to attack this problem as a compressed sensing problem with this type of dimensions is absolutely impossible, because the ambient dimension of these problems for anything that looks like practical is just too large. However, there is this connection. And then, thanks to this connection, some people have proposed what they have called coded compressed sensing. So the idea is that we take a message of 100 bits, say these are our B bits, but then we split it into subblocks. So these subblocks in this case are called W0, W1, etc. And then we create a code, an outer code that works as follows. The first block is simply contains the bits, the information bit of just copied like that. But the next block, they all have the same length. I call this length J. Okay, J, J, J. The next block is obtained by taking fresh information from the block W1, but appending some L1 parity bits, which are in fact a function of the previous block. And then I keep going like this. So at every block, the parity bits are functions of all the bits that have appeared before in the previous blocks. So now I have these encoded blocks of same length J. So I can use this idea of compressed sensing for every section. So in particular, you know, I will use these J bits to select one column of a matrix which is of dimension n times 2 to the J. And basically this will be repeated for a number of times. So in this way, for example, if I take you know, J to be, I don't know, some number, for example 12 or 14, so this number 2 to the 12 is much more, or 2 to the 14 is much more feasible. So this problem breaks, so this approach breaks this problem into a sequence of subproblems. And why we do this outer coding? The outer coding is done in order to somehow stitch the messages together after decoding every slot, because what happens here is that a compress sensing decoder will find which are the ones in each subblock, so which messages or sub-messages are active in each subblock. But then, in order to recover the whole message, we have somehow to stitch them together, because the compress sensing will come up with a list of possibilities for the first slot, a list of possibilities for the second slot, a list of possibilities. This is simply given by the support of the estimated vector. There are ones, so it's a list of possible messages, but then we have to be able to stitch them together. And because we have this sort of hierarchical generation of the parity bits, you see that there is only a few possibilities for this message to generate this. You can interpret this as a sort of hash function of these bits. Every parity is like a hash function of the previous bits. So basically it means that given a decoded message here, there is only a small number, hopefully a small number of branches that are valid, and then by basically going on, at the end the decoder will be able to find a path, a feasible path in the tree, and somehow stitch together all these messages. So in this paper they have analyzed especially the behavior of this outer tree code, and find out in which conditions you can actually do the decoding with high probability, and of course this is a function of the rate of the code, which is how many parity bits you plug into every slot, and also how you distribute them, because there is also a trade-off between rate and complexity. It turns out that in order to maximize the rate, it is better to have all the parity bits at the end. So, and so basically keep open all the path and then just resolve them at the last step. But in this way, the tree grows exponentially. So in fact, there is a trade-off. You need to be able to kill enough number of possible paths at every stage in order to keep the complexity under control. And so there is like an optimal parity distribution across the stages that these people have studied. Okay, so this idea basically decomposes the original problem into a sequence of compressed sensing problems that are much more manageable, and then there is an outer code that puts these things together. Now we get to something that we have done. So it turns out that some people, much before all this story became in fashion, proposed a coding scheme that goes under the name of sparse superposition code, or SPARCS, which is in fact very ingenious, and they also were able to prove that this coding scheme achieves vanishing probability of error at rate up to capacity for the Gaussian channel. And the coding scheme is a purely single user coding scheme. Let me try to explain it in a very simple way. So basically it works like this. They construct a matrix with Gaussian IID columns, and this matrix is divided into sections, into L sections. And then they simply encode information by taking a vector here, divided also into L sections, and putting a single one in each of the sections. So this is a highly sparse vector, but it is a structure.
Giuseppe?
Yes?
That's why I wanted to ask a question. Yes.
I just wanted to ask a quick question, if possible. Sorry.
Yes, sure.
Do you have design control over this M by 2 to the B matrix from the previous example, or is it given to you?
No, you have full design control.
Okay.
This is a coding matrix. You can design it as you like.
Okay, so the issue here is about the runtime of trying to decode with a matrix of that size, I guess.
Yes.
Okay.
Yes.
All right. Just wanted to make sure.
Yes.
Thanks.
So basically, I was saying the code is the code word. The transmitted code word is just the product of this matrix A times this vector, the vector B. So essentially, is simply the superposition of the column picked in the first section, the column picked in the second section, the column picked in the third section, etc., etc. And they prove that the section error rate can be made as small as desired for all the rates less than the capacity of the Gaussian channel. And of course, they say, okay, when you have a section error rate is basically you make an error when, by detecting a section. And then you can always, when you have a vanishing section error rate, you can put an outer code that basically of arbitrarily high rate that cleans this residual section, this vanishing residual section error rate. So the fact that the encoder has this linear structure make us think that this is in fact a very good candidate for the unsourced random access, because what we can do effectively is to basically give to all the users the same spark. So instead of breaking the problem into little subproblems as before, we simply break it into different sections of the same spark. So basically what we can do is, this will be a vector that contains a message for user K and encode it into the position of these ones in the sections, but the coding matrix is the same because all the users use the same code book. So this means that combining the linearity of the encoding with the linearity of the multi-access channel, what happens here is that basically what we receive is in fact the same coding matrix multiplied by the sum of these vectors. So what happens now is that now these sectionized vectors, instead of having a single one in every section, they can have multiple ones, and all since they all can also overlap. So in general, they have up to Ka non-zero components, but they could be less. And in fact, the distribution of these sections is multinomial. So multinomial distributions are complicated and a complicated, discrete, multidimensional distribution. So what we did, in fact, is to basically, first of all, recognize that we can think the problem as follows. We have a single user type of compressing type of problem where we have this theta is the vector or the superposition of all these sectionized vectors, and then simply we observe a theta plus z, and we want to reconstruct theta. And theta is sparse, although it is not constrained to have a single non-zero per section, but still under the we will see what is a good prior distribution to make a nice algorithm with good properties. Then once assuming that we have reconstructed say theta faithfully, then what we have in fact at the end is a binary input other MAC, where basically if this is the support of theta. In fact, we can even simplify the problem and use a so-called OR channel. So if we just quantize the zeros and the non-zeros to be 0 and 1, we have an OR channel, and OR means that the output symbol is 1 if the OR of the input symbols is 1. So it means that if there is only one user, or one or more users that are acting on a certain symbol, you see that one at the output. The nice thing about the OR channel is that it is a problem that has been widely investigated because it's very related to group testing. You see like this. I imagine that I have a binary vectors, right? Like this, and then I have another one like this, and then another one like this. And then I do like the bitwise OR. So I have a 1 every time I have at least a 1 in these rows, like this, right? And now you may imagine that. So the idea is to find, you know, all the code words that are that give that are covered by this code word, and somehow there is a under certain condition on the rate, you can actually find all the code word individually. And this is very related to group testing because, you know, if you have a condition, for example, infected, non-infected, and you start creating this different random pooling of your measurements, or typically it was done with the blood test. And then if there is a sample which is infected in the whole pool, it will mark as infected. And this is the OR, the logical OR of the condition being infected. And so this problem is exactly related to group testing, for which that has been widely studied. So we know a lot of things about this. So for the inner code, which is basically going from this observation to reconstructing this sparse vector, we can use the so-called approximated message passing algorithm. And the approximated message passing algorithm that we propose is well, it's a well-known Bayesian algorithm to solve complex sensing problems that can incorporate arbitrary priors. This is the recursion, is based on a function which is in fact the minimum mean square error estimation of the symbols you want from observation that takes on the form of essentially the so-called decoupled channel model. So when you observe that symbol alone with a certain Gaussian noise of a given variance, and so what we can do is to write down this will be this of course non-linear, because the symbols are zeros and ones. Actually, they're integer with this multinomial distribution. But this makes things too complex, because so we basically look just at the marginal distribution. The marginal distribution is binomial. So these probabilities are binomial, and this is exactly the minimum mean square error estimates of estimating basically if observation like this where this x is binomial, and then here we have square root of, actually not square root because there is tau square, so I should write tau here, tau z. And this is Gaussian 0, 1. This tau depends on the iteration and is something that can be recursively computed. And then and these are the prior probabilities of these binomial random variables. Basically, this algorithm not only works very well, but can also be analyzed through a technique called density evolution, which is in fact asymptotically exact for large dimensions when the matrix is IID sub-Gaussian. So if the background noise is in this model, when the background noise is Gaussian and the matrix is IID sub-Gaussian, and for arbitrary distribution of theta, the density, the state evolution of approximated message passing becomes exact for large dimensions. So we can exactly characterize the performances of this algorithm. And I will We can also use techniques based on basically the replica method of statistical physics to characterize the performances of a non-computable but surely symbol-wise optimal algorithm that is the so-called symbol by symbol maximal posteriori probability estimator that decides for the symbols by maximizing the posterior probability given the whole vector observation and of course the sensing matrix. This is non-computable because computing these posterior probabilities means marginalizing over an exponentially large number of terms and is essentially infeasible, but we can still characterize the performances of these without using these statistical physics techniques. And and basically at the end what happens is that there is a theorem that says that in the limit, so we fix the inner coding rate, we fix the total spectral efficiency and the so-called energy per bit, and in the limit for basically the number of sections and block length go to infinity for fixed number of bits per section, and therefore fixed inner coding rate. So essentially this means that the ratio ln remain fixed because this is a constant, this is a constant, so ln go to infinity but at fixed ratio. It turns out that under this condition there exists, one can calculate functions that we call E optimal and E algorithmic, such that if the energy per bit is greater than E optimal, then the probability of error of the maximum posteriori probability detector can be made as small as we want, and if the energy per bit is greater than E algorithmic, then the probability of the AMP can be made as small as we want. And these two functions are very complicated, are given through implicitly to fixed point calculations, and you have also to pick the fixed point that minimize a certain profile, which is called the free energy profile. So it's too complicated to write, but this can be done and can be proved. So this basically give us the asymptotic performance of the inner decoder. And this is just a simulation that shows, of course, this is an estimate of these symbols, and then we have still to decide whether they are zeros or they are ones. So because AMP gives like a soft estimate, then we can threshold this soft estimate, and therefore we can with this threshold we can get a receiver operating curve by trading off between false alarm and misdetection probability. Misdetection probability is when we do not detect a message that was transmitted, and false alarm is that when we detect a message that was not transmitted. And clearly the misdetection probability is to be taken into account especially carefully, because then we have the outer code. And if the list does not contain a message that was transmitted at a certain slot, the outer code gets into troubles. It's not able to complete the path in the tree. If the list contains some spurious messages, is not so terrible, because with high probability these messages will not be selected because they will be incompatible with the parity bits of the previous messages. So in other words, it's always better to operate at small probability of misdetection and be a little bit more generous with the probability of false alarm, thanks to the outer code. But of course, in practice, when we work at a finite dimension, we have to always to optimize these things very carefully. This is just a general reasoning. So basically, then we can go to the OR channel, the OR channel where we can see all these binary vectors with a single one indicating the message transmitted by the active user K, and we take the OR bit a bit, and then the outer code has to find which messages were transmitted from the OR beta bit. Of course, it's impossible if you have no redundancy, but thanks to the fact that the code, there is a code for the OR channel that works not at full rate, not all possible combination of messages are possible, it is still possible to decode. And in fact, one can show that the condition for decoding is an if and only if, is that the mutual information between this binary vector and the decoded vector, so the OR of this binary vector, divided by the total number of dimensions here, and user must be less than the rate of the outer code. So one can elaborate this mutual information. It takes a while, and I will not get into the details. It's in the paper. But it turns out that if we pick J to be alpha log Ka, and then Ka becomes large, J becomes large with the logarithm of Ka, and alpha is a number greater than 1, it turns out that basically this quantity is upper bounded by 1 minus the probability of misdetection of the inner code times 1 minus 1 over alpha. And now we know that we can make this probability as small as we want. So at the end of the story, it turns out that by putting everything together and picking the outer coding rate in this way, we can show achievability results of a certain spectral efficiency for in the regime of small signal to noise ratio, but fixed EB over N0, because of both the rate and the power go to 0, but the number of energy, the energy per bit remains constant, and we can characterize achievability results for both the optimal maximum a posteriori probability inner detector and the practical approximated message passing detector that says essentially a positive result that says essentially that this system is able to communicate at a non-vanishing total spectral efficiency and with arbitrarily small probability of error. Good. So in the remaining maybe 15 minutes, I would like to talk about an extent.
By the way, we have just gone over the hour mark. I don't know if you want to.
Oh, that's right. Sorry, it's already 9:30. I thought we started at 9. I thought I still had a. Oh. Okay, you're absolutely right. So I should be quick.
Okay, cool.
Well, okay. So let me just say one thing, maybe two small things. This problem we have proposed an extension that has catched quite a bit, caught quite a bit of attention, and this is the multiple antenna case. So in the multiple antenna case, essentially is as before, but now what happens is that so before we had imagine time runs vertically, and we have this code word, say A, K are this code word like this of. But now we also, instead of just having one symbol per time slot, we also have many antennas. So we can, what we receive is in fact the outer product of the code word over time and a raw vector that contains the coefficient of the antenna. So we receive basically a big matrix, which will be the sum over the users, and there will be noise here, and this dimension is time, this dimension is antennas. And this problem is very nice because it has the following structure. Has the structure of basically a so-called multiple measurement vector in compressed sensing, where we can see the coding matrix is again here. Now, instead of having just a sparse vector, we have a sparse diagonal matrix that will simply basically weight the rows. We have a non-zero row in correspondence of an active users and 0 rows in corresponding of a non-active user. So if you look at this matrix, each one of these vectors is a sparse vector with the same sparsity pattern. And it turns out that in this problem, we have essentially 3 regimes. We have the regime of compressed sensing, where we have enough dimensions in time for which the typical example, number of measurements larger than number of non-zero. So number of measurements, which is this dimension should be larger than the number of non-zero, which is the number of active users. This is L, this is the number of active users, times a fudge factor, which is logarithmic. And this is the classical compressed sensing regime, in which we not only find who is talking, so which message is active, but also we can also estimate these vectors, because in the compressed sensing regime you really estimate the sparse vectors. So you can also get the so-called channel estimation if you want. Then there is a regime in which the number of measurements and active users are linearly related, but this inequality does not hold. So this goes beyond the compressed sensing regime, but we can still find the sparsity pattern with high probability. And this is a bit counterintuitive, but for sure we will not be able to estimate these vectors, but we can still find the sparsity pattern. And then there is what we call the identifiability regime. And the identifiability regime essentially is the regime where basically we can identify, if you go to the covariance case, so you go to y transpose, and then divide by the number of antennas. This is the sample covariance. Basically, what you can get essentially the eigenvalues or the singular values of the covariance and give you the active users. And it turns out that in this regime you can find reliably the number, the sparsity pattern, as long as the number of active users is less than the square of the dimension, which is much better than linear. It means that you can really afford an enormous number of active users. So it turns out that, well, of course I don't have time anymore, but it turns out that what we can do is, first of all, we have proposed an algorithm which is based on maximizing or actually minimizing the negative likelihood function for this parameter. So it's a non-Bayesian algorithm. And there is a simpler version, which is simply a non-negative least squared problem. And it turns out that these things can be analyzed, and we can get, in fact, a scaling law that tells us exactly when this non-negative least square problem gives the right solution, under which type of scaling in terms of number of time dimensions, number of antennas, and number of active users or number of active messages. And the algorithms are not that complex. We can also simulate them. Is actually doable. We have these the scaling laws are even visible. You can have a relatively sharp phase transition where you can see this quadratic behavior between the feasibility and infeasibility region. And also we can also characterize the scaling law or the total spectral efficiency of these systems, that becomes essentially it increases as log L log L, where L is the number of symbols in time. So of course the number of bit per, rate per user goes to 0, but overall the system can have a fairly large spectral efficiency. And finally, it's very interesting to see, okay, here we can, for example, see simulations and see error probabilities. This is all done with our simple algorithm, which then it turns out to be a special case of something called the sparse Bayesian learning that other people have proposed in a different context, but in fact is almost identical. So we realized this after some reviewer made the comments, unfortunately, but okay, still the paper is valid because of the analysis. And what is most amazing is that some colleagues, in particular Wei Yu from Toronto, they have come up with a completely different way of doing the phase transition analysis for this problem, which is based on the properties or the asymptotic properties of the maximum likelihood estimator. And so by analyzing the Fisher information matrix, and they can even find an algorithmic way to generate the asymptotic statistics of the estimation error, for which one can, simulate the scheme and compare with the simulations. So they have essentially validated our scaling laws and also give an analytic tool to artificially generate directly the statistics of the maximum likelihood estimation error. So this is all very interesting. There is a connection with the rank 1 tensor decomposition, because if I write this channel as y equal to sum over k, and then we have these code words times the channels transpose plus noise. Now you see that if we vectorize everything, now vec of a k h transpose becomes a Kronecker h. So some people recently have proposed to construct this code word as essentially take subcodes and construct code words by taking Kronecker products of smaller code words. So at the end, the whole thing put in here becomes, if we have a D-level rank 1 tensor here, and then the channel, which is unknown, and so we have a D plus 1 level rank 1 tensor, and then basically the identification of the users and the decoding can be cast as taking this matrix and finding a rank Ka, so it's the number of terms in the sum, D plus 1 level tensor decomposition in the presence of noise. And this is, in fact, there are results on the uniqueness of the tensor decomposition, but they are noiseless results. So the problem here is robust tensor decomposition, and what are the conditions or the scaling laws for which this can give vanishing probability of error or small probability of error. And then this is pretty much, I think, a very interesting problem for the future, and it seems to be also quite promising. So altogether, I'd like to conclude. Admittedly, it was a lot of stuff, but I hope to have conveyed at least a few ideas and some connection with mathematics that probably is more appealing to mathematicians, like, for example, compressed sensing and approximate message passing and low rank tensor decomposition. Thank you.